So our goal here is to expedite particle accelerator optimization and maximize the control and tuning by developing algorithms that learn like a living being. And I'll explain in the next few slides what does it mean to learn by a living being. So when optimizing an accelerator, the operators take several tasks. And one of the most consuming tasks is quadrupole tuning, which roughly takes 15 minutes in the setup. And the search space is pretty big. It's around 24 dimensions. We also have configuration change 2 to 5 times per day. And with each configuration change, everything needs to be retuned. And typically, specifically for the quadrupole tunings, we use simplex algorithm, and we optimize down the Linac. And we're starting with the upstream quads. We optimize group of quads, as you can see here. And by optimizing down the Linac, we increase the pulse intensity of the X-ray. And it takes roughly 15 minutes, as you can see here. With LCLS2, things are going to be much more frightening because there are going to be many more dimensions or many more controls to tune on. So let's quickly review what are the optimizers that are available to us. So I'm sure most of us are familiar with this diagram where artificial intelligence contains machine learning and contains deep learning. And basically what people think about artificial intelligence is that we try to teach the machine some sort of, to exhibit some sort of intelligence like reasoning. In machine learning, we typically give the computer data to learn a representation in order to do some tasks, for example, optimization tasks. In deep learning, it's type of machine learning where we are inspired by our own brain's neural network, and people mostly refer to this as deep neural networks. And intersect with each one of those sections is the mathematical optimization. So here we have the simplex algorithm or gradient descent. In the intersection with AI, we have evolutionary algorithms like genetic algorithms, and the intersection with machine learning, we have Bayesian optimization. Now let's divide those algorithms into two different optimizations. The first one is model-based, and the second is model-free. So in model-free optimization, we have either global optimizers like the genetic algorithms that are showing here, or local optimizers that are part of the mathematical optimization. In model-based optimization, we either have deterministic optimizers where we fit model to data, or we can take a Bayesian approach where we calculate probability over functions given that data. And of course, we always remember that we have our human optimization right here. So why did we choose Bayesian optimization? So on the one side, we have human optimizers where we are lifelong learners and we have experience, we learn from experience, but sometimes we suffer from mental modes and we make relatively slow decisions. On the other side, we have numerical optimizers where usually they learn with bulks of data, oftentimes cannot estimate uncertainties, but they can juggle many things at once and make fast decisions. So model-based Bayesian optimization combines the complementary strengths of both approaches. And the reason we chose Bayesian optimizer is because of a good regulator of the system is a good model of that system. So let's see how it works. Bayesian optimization is a gradient-free approach to optimize expensive to evaluate system, and it learns by experience. So let's see, we have some input controls, we apply them on the machine, we look at the output, and then we think and we suggest the next set of input to try on the machine. And like this, we go iteratively and tune the different knobs until we are happy with the results or until we reach a computational budget. Now, Bayesian optimizer does exactly the same. But how the optimizer suggests the next set of inputs? Well, it uses a utility function or an acquisition function to do that. But how exactly this acquisition function decides where to choose the next point? So let's get some intuition to that. If I have an unknown function here, which I sampled 4 points, and I would ask you, where is the maximum of f, and where should we take the next evaluation in order to find this maximum? So probably you would tell me, okay, D, if it's a linear function, so maybe better to take the next evaluation here. But maybe it has this form of function, and better to take the next evaluation here to find the maximum, or maybe this one, or maybe that one, or even if we take 100 models, we have this one. And I think you understand where it's going. In the limit of infinite models, we can get something called here a Gaussian process, where this is the mean of the Gaussian process, and this is the uncertainty interval of that Gaussian process. And basically, we use this as a surrogate model in order to inform the acquisition function where to choose the next input controls. Sorry? Okay, so let's continue. Here we have unknown objective function. This is it. We build a probabilistic model. We use Gaussian process. Here you can see the mean of this Gaussian process and the uncertainty and few samples from that process. Then we measure 1 point on the machine, which includes quadrupole and FEL energy, for example. Here it is. I measured it, and then I update my model. Then I choose the next point to sample to simultaneously increase the objective and decrease the model uncertainty. And this is the acquisition function we chose to use with upper confidence bound, which basically just takes the mean and some beta of the uncertainty. And this acquisition function, maximizing it, suggests that this point needs to be measured next. So we measure it. Here we sample it and we update our model, and then we do it iteratively for the steps, and this should be the next point to sample, and this would be the next point, etc., etc. So in a continuous way, it would look like this. So you can see again that the Bayesian optimizer wants to exploit the region where it thinks the maximum is, but at the same time, we would like to explore new regions where unexpectedly we might have a higher maximum. So in Bayesian optimization, it's all about the gentle balance between exploration versus exploitation. And we take care of that by tuning the right hyperparameters. So for the surrogate model, we chose Gaussian process, and Gaussian process is just an infinite dimension Gaussian. And rather than having a normal distribution with mean and sigma, we have a distribution with mean function and covariance function. And this kernel function or covariance encodes the smoothness between 2 points. So here is an example of 2 different covariance functions. One is the popular radial basis function, one is exponential kernel, and you can see that the smoothness of the Gaussian process looks different between those 2 samples. And there are a few reasons that we chose GP, and the first one is that we can shape our prior belief about the system by choosing the right kernel function. The second one is that sometimes maybe the optimum moves day to day, but the kernel captures the shape. So as long as the shape remains the same, we're good. And the last thing is the inherent property that the GP has. They give reliable estimate of their uncertainty, as you see here in the shaded blue. So for the work I'll present next, we chose radial basis function kernel, which has this form, plus noise kernel. And highlighted here in the different colors is the different hyperparameters that needs to be tuned. So we have amplitude of the kernel, we have this precision matrix, which is basically a diagonal matrix of the inverse length scale squared. The length scale is the parameters that responsible on the smoothness between two adjacent points. You can see here for shorter length scale, we get more a more wiggly process with wide confidence intervals. But for a longer length scale, we get a more coarser approximation of our objective. So we've got all those hyperparameters, and now we need to find them. So the way to do that is by estimating them from the marginal likelihood, or sometimes called ML type 2. We want to maximize the marginal likelihood, and the combination of the hyperparameters that maximize it, this is the one that we choose to run the kernel with. So here I show an example. This is the precision matrix. This is 13-dimension control, so 13 by 13 matrix. It is diagonal. All these different length scales are the ones that maximizes the marginal likelihood of the model given the data. So this is how we did it for LCLS, and now we want to use this. So our goal here is to optimize the FEL pulse energy with respect to 12 quadrupole magnets. And we chose the probabilistic model, we chose the Gaussian process, we chose a kernel, we chose hyperparameters, and we use the OWLE framework, which is just a GUI to control batches of devices with various optimizers. It was developed in collaboration with Daisy, and here is the GitHub link where you can download and play with it. And the optimizer connects between the machine interface and the algorithm API, and this is how it looks like. So with this in mind, we maximize the pulse energy, as you can see here, with the GP much faster than using simplex. And the GP reaches a higher optimum than simplex. Those, the 12 quadrupoles that were used are those here in red. So, sorry, and we also verified it in simulation. So this work was done with a diagonal kernel, and then we said, okay, we want to have maybe a correlated kernel, so having an off-diagonal elements, because the optimization might be faster. So let's see here a toy example. If we have a synthetic ground truth which is correlated, using an isotropic kernel could bring us just as fast, but using a correlated kernel could bring us much faster. And this difference, this is on the y-axis, is the mean number of steps to convergence. So the correlated kernel takes less numbers to converge, and this difference is enhanced as we go to higher dimensions. Okay, so now we wanted to include those correlations. So this would mean in the precision matrix to have these off-diagonal elements here. But unfortunately, although we knew that they exist, we could not resolve them in the data. So you can see in this plot the correlation coefficient versus electron beam energy, and there is no clear trend in the correlations between two quads in different scans, although we know that two adjacent quads should be anti-correlated with respect to each other. So the way we determine those correlation is from a physics simulation, and we calculated the correlation from the simulation, and then we incorporate them into the precision matrix. and we demonstrated on 4 quadrupoles. So you can see that Gaussian process with correlations performs faster than Gaussian process without correlations. So this work was led by Joe Doris from SLAC, okay, and at this point we made a correlated kernel, but we had to use data from the machine. So the question is, can we tune both length scales and correlations from simulation in a faster way? And this is what we call a physics-informed kernel. And this is cool because we don't need any archive data. So this could be suitable for new machines where data is not available. So the kernel could either have a closed form as the RBF kernel that we saw, but it could also be defined as a convolution of basis function. So this is the convolution, and this basis function is approximated from a simulation or an analytical model. So for example, in Sphere 3, we have beam loss rate versus quadrupole, and this is typically the shape of it. So we can say, okay, we could choose maybe rational quadratic or Matern kernels to capture this shape. But we could also calculate this basis function of the simulation and compute the kernel. So the way we did it is we expand the simulation around the peak using a Taylor expansion. So the gradient is 0 because it's around the peak, and then we left with this expansion where x0 is the simulation peak and h is the Hessian around the peak. We calculated the Hessian in 2 different methods. So first we had a surrogate model of this objective, and we calculate the Hessian on the surrogate model. And the second way we calculate this Hessian was using the simulation directly and numerical differentiation. And then from this basis function, we computed the autocorrelation, and we got this kernel function where now this precision matrix is negative the Hessian divided by 2, and you can see that it has not only the diagonal but also the off-diagonal elements. So in a faster calculation, we got all the matrix from a physics simulation. Any questions so far?
Yeah, I have maybe a question, Adi.
Yeah.
So yeah, it's very interesting. One way in which people sometimes try to infer the length scales in the kernel is by using maximum likelihood, and
right.
And the way you describe how you get the length scale here is different. So I guess my question is there a problem with using maximal likelihood in this particular case?
Is there a problem? Sorry, say again.
So could you have used maximal likelihood to estimate those parameters as an alternative to what you're doing now?
Right. So maximum likelihood estimation, as I showed, we did for LCLS here. For this, we need tons of data. So if you have archived data, then you can learn the hyperparameters from the archived data. If you don't have any archived data because you're in a new configuration or new machine, then you can generate a lot of simulation data, right? But this is computationally expensive. You would want to use the simulation in a wise way and just to calculate the few points that are needed for the Hessian, for example, rather than having raster scans of the simulation in order to estimate the parameters.
Okay, makes sense.
Yeah, and another thing is that with the ML type 2, people usually train only diagonal kernels, and baking in the correlations into it from simulation or learning correlation using ML type 2 would require much more data. And you want to be data efficient, right? You don't want to spend now too much time on just generating simulation data if you can use the simulation directly to calculate the kernel function.
Okay, thanks.
Yeah, sure. Thank you. So with this in mind, we calculated.
Sorry to interrupt. Hello.
Yeah.
Yeah, so I wanted to ask, like, if you go for a non-diagonal elements kind of model, like in which you have some non-diagonal elements as well. So, like, how do you ensure like the covariance would be or the covariance matrix or the inverse of the precision matrix would be positive semi-definite? Do you ensure any extra like constraint on them?
Yeah. So by calculating the kernel from the autocovariance and by assuming that your model or your simulation is convex and monotonically decreasing, like we have in the example here, you're assured to get a positive semi-definite kernel. And thank you for that note. Kumar?
Yeah, I am there. So
Okay.
yeah, I thank you for explaining that.
Okay, great, thanks.
Sorry.
Mhm.
Sorry.
Yeah.
So if I understood correctly, so this only works for the region around this maximum. That means that's more or less also a local search.
So you want to find the optimum of your system online. So we estimate the kernel and the hashing around the optimum of the simulation. But then, as I'll show next, we started our optimization far from that peak. So this basis function that you see here with this Taylor expansion is a good approximation of this objective, also far from the optimum, because because of the shape of this objective. For other objectives, this needs to be investigated, but for convex functions, monotonically decreasing, where the second derivative exists, so this is a sufficient formulation in order to find the basis functions and to assure that the kernel is positive semi-definite.
Okay, thank you.
Thanks.
Just to another clarification on this point, could we do we need to ensure again the monotonically decreasing nature of the function f or convexity of f? Like, how do you ensure it, or is it automatically ensured?
So it depends on your objective function. We chose an objective function that could be approximated by a Taylor expansion and up to second order in log space. So this assures that the basis function would capture exactly the shape of the objective, not just locally, but also far from the optimum. So
Okay.
for those cases, it works. For other cases, we need to calculate different basis functions and make sure. But this demonstration is only with this type of basis function.
So what is the function f that you are using?
Sorry, what is the what?
What is the function f that you are using?
Oh, the f in this case would be our MATLAB simulation of Spirit Tree storage ring, which I was about to show here. This method was demonstrated on the Spirit Tree storage ring to optimize 13 skew quadrupoles. to tune 13 skew quadrupoles in order to optimize the beam loss rate. And this is what I'm showing here. We see that we want to maximize the beam loss rate. And you can see here that online on the machine and also in simulation, Gaussian process with the physics-informed basis function converges faster than GP trained on archive data with ML type 2. And also, please remember that the red curve is GP with only a diagonal kernel, whereas the blue line here is a GP with a full precision matrix, so also correlations included. And both GPs perform much faster than RCDS and simplex, where each step here is 2 to 3 seconds for simplex and GPs, and for RCDS we had to use longer, 6 seconds per step, in order to average the noise better, so RCDS could deal with it better. So overall, with GPs, we got 10 times speed up, and GP with correlated kernel from physics, we were able to even get a little more speed up. In simulation, we found even a higher optimum with physics-informed GP. Another point that I wanted to show here is the effect of the GP prior mean. So remember, we saw a few slides ago that the Gaussian process has mean function and also kernel function. So in our case, the beam loss rate had an offset of the gas scattering background, which has some value of 0.3, so it's not 0. And if we use a Gaussian process with 0 prior mean, showing here in dashed line, it converges slower to a lower optimum. And if we use the right value for the prior mean, which is equivalent to this offset, to this asymptotic value here, we got a GP converge faster. And for 0 prior mean or non-zero prior mean, the physics-informed GP converge faster than the data-informed GP, as you can see here for each method. So this is the effect of the prior mean. Then we took this GP method and we applied it on PEGASUS on making flat beam. And when making flat beam, we actually have a 2D objective function, but we folded it into a 1D objective, calculating just the ratio between sigma x and sigma y. And flat beams are important for slab structures, for example, for the electric laser accelerators. We used RBF kernel learned from simulation, and we set up this remote control room between SLAC and PEGASUS lab way before it was trendy due to COVID-19. And in collaboration with Eric Kropp and Pietro Mussami and Orly Edelin and Claudio from SLAC, we demonstrated that the Gaussian process converged faster on flat beam than extreme seeking, and you can see that the quality of it is even a little bit better than hand tuning. This is how it looks like. The objective x over y, we can see the GP converged here. When we started from a further initial point, so you can see this initial point is much blurry than this one. ES failed to converge, where GP was able to converge on a nice flat beam. And a very nice thing is that we ran everything from a laptop, from a Jupyter notebook, and we were able to interact with PEGASUS remotely. And this is a nice feature of the PEGASUS lab that allowed us to connect, to talk to the controls and to read from the database remotely. Then we took this method and we also applied it to ANL in maximizing the APS Linac charge. Typically, there are 16 magnets here showing in blue, and 4 of which are steering magnets. And using simplex, it usually takes 30 minutes. And because of the magnet's hysteresis, as you can see here, we need to use a smaller step size. So this even takes longer. So another solution is to manually fine-tune the charge after the optimizer. So we applied the GP to it. We used RBF and Matern kernels, learned from raster scans, so using ML type 2 here, trained on either 12 or 16 magnets. We had to wait until the readback is equal to the set point, because when the step size was too big, the magnet's response time was longer. And you can see here that the GP we tried different types of hyperparameters. None of them reached to 1 nanocoulomb, which is the maximum available. And basically, GP on average performed as well as RCDS here. So this is a lesson to show that tuning the hyperparameters is super important in order to maximize the potential of the machine. And just to summarize this part, we saw a Bayesian optimization using Gaussian process on LCLS, Spirit3, PEGASUS, and ANL, where we maximized or minimized 1D objective using tens of controls. We saw the physics-informed GP, where we used simulation to inform the kernel selection. And we saw the basis function kernel, which is a faster method than the alternative ML type 2 using data. And the one takeaway from here is that physics-informed basis function kernel is cool, because we can tune new machines without any archive data, just based on prior simulations. And are there any questions on this part before we switch gears to anomaly detection?
Maybe a quick question on drifts.
Yeah.
So some machines drift over some time scale. So I guess the question is, how long do you keep the Gaussian process running until you maybe have to reset it and have it forget the previous data points, basically start from scratch again?
Yeah, I think that the idea for the Gaussian process is to tune as fast as you can, and then you can sit there. And then when you're not happy with with the output and you feel that you need to retune, you just restart the GP with a new model. You forget about the previous observation, because then you want to count for the drift. And the way that you can see if you have a drift is by using the anomaly detection using Gaussian process, which I wanted to show next, unless you have another question.
A great transition then.
Yeah. Yeah, thanks for the question, Ron. Okay, so let's see. Anomaly detection, why do we need this? So there are failures on the accelerators, there are trips or slow drifts, and in order to find those, the operators need to chase logbook entries. This results in downtime and unhappy users. But if we detect and ultimately forecast those failures, we can increase the operations and data system reliability. So our goal here is to have a timely identification of anomalies and forecasting. And our goal here is really to find observations that deviate from normal behavior. And here we can see various types of anomalies. So we can either have a global outlier, we could have a level change, we can have a pattern deviation, as see here, or pattern change. And the method we use here is to fit two Gaussian processes, one that accounts for short-term variation and one that accounts for the long-term trend. And the way we do it is with each data point here in time, we add it to the GP model. We refit the Gaussian process with short-term kernel, long-term kernel, and noise. And we calculate the derivative of the GP, of the short term of the GP. This goes to rate of change. And the variation around the trend here is the deviation from the GP fitted with the long-term kernel. So each point here is then being classified using the fitted GP and its derivative to this 2x2 matrix. And this matrix is actually an idea taken from business and economy, where they track on stock exchange and trends in the market. The red box right here, it means that we are above trend and we keep increasing. So this is an anomaly that's going to explode. The green block here means that we are below trend and decreasing. So again, we are going below some acceptable threshold. The yellow here, it means that we're below trend and increasing, so go back to normal, and same with the orange above, but decreasing, go back to normal. And we can decide about some normal boundaries here, normal box that we can tolerate those machine variations. So let's see how it looks like on a toy model. On the top, we can see a normal signal. On the bottom, we can see a drifted signal. And you can see that there is short-term and long-term GPs here. And when the signal started to drift, we can see this blue point go outside of the box into the right because this signal is above the trend. Now the signal will go down below the trend, so it will go here to the left. And in the normal case, it always stays within this gray box in the middle. So this is normal. So this is on a toy model, and then we applied it to experimental data from LCLS. This is a fault in the X-ray pulse energy that caused 5 hours of downtime. You can see that the X-ray pulse energy dropped to 0 and then went up a little bit and then again to 0. And we can see here those A, B, C, D points mapped into this 2x2 matrix to A, B, C, D. A is normal, so it's going into the normal box. B, C, and D are here, so they are anomalies. They go outside to the box. So this is detection. In order to do prediction, this is just an additional step using the GP property that we can get the surrogate model in points that we did not observe any data. So for the prediction, we would utilize the next 5 seconds from the GP model to forecast an anomaly. But we haven't implemented this step yet. This is an ongoing research. And with this, I would like to thank you and acknowledge the support from SLAC and from Oscar. So thanks everyone, and I'd be happy to take questions.